Hello and welcome to Lecture 8, where we're going to look at further aspects of FM and PM. In particular, we'll look at the bandwidth and demodulation of FM. So in our last lecture, we introduced angle modulation. We spoke about FM and PM and how it's generated. We introduced the idea of the instantaneous frequency and instantaneous phase. We spoke about frequency and phase deviation, and we introduced the idea of the depth of modulation or modulation index for frequency modulation, where the amplitude of our message is encoded not in the amplitude of our high frequency carrier, but in the instantaneous frequency. So you have high frequency and low frequency corresponding to our message. So today we're going to be talking about bandwidth. So a lot of today's lecture will be talking about how much bandwidth FM takes up. We'll introduce something called Carson's rule for estimating FM bandwidth. And we'll spend a little bit of time talking about demodulation. Even though demodulation is the title of today's lecture, we're going to spend a little bit more time talking about FM in general, about the bandwidth of FM, and about the future of FM. Next week, we'll be talking about digitization, because that is the bridge, if you like, to the latter half of our module, where we're going to talk about digital communications. So these three lectures are digital communications, and digitization is the bridge from analog to digital modulation. So you've already finished test 1. The only assessment that remains before the final exam is your second class test on the 12th of May. So a quick recap. When we spoke about FM last time, we introduced the idea of phase and frequency, and we said phase is the integral of frequency, and frequency is the derivative of the phase. So you have your angle and you have your message, and the angle is some function of the message. Now, if that function is an integral, then we have FM, and if it's just some multiple, then it's PM. We introduced the idea of instantaneous frequency. That's the frequency at any instant in time, and we said that for FM will be the sum of the carrier frequency and some scalar constant multiplied by the amplitude of your message. So M of t, that's your message. That's your baseband modulating signal. Okay, so as I said, today we're going to be talking about bandwidth, and we're going to be talking about demodulation. So these are the a bit of terminology. We've already introduced these constants before, the Kf and Kp. Now, even though these appear here, we won't be using these because these all get rolled up into our all-important modulation index, which is the ratio of the frequency deviation and the baseband bandwidth. So the baseband bandwidth, that relates to, so that's FM, and that relates to your message. Whereas the frequency deviation, that's delta F, and that relates to your bandpass signal, because that's a deviation from the carrier. Now, there's also something called the frequency swing, which is twice the frequency deviation. So, for example, if you have a carrier frequency of 100 megahertz, and you have a frequency deviation of, let's say, 100 kilohertz. Now, because you have that deviation on either side of the carrier, you have that same delta F, then we refer to this as the swing. Okay, so you've got 2 delta F, and we call that the swing. So the swing is twice the frequency deviation. Okay. Now, in AM, whether it was DSB or SSB, we always knew what the bandwidth was. It was either twice FM or 1 times FM or something between 1 and 2. But for FM, it's less easy to calculate the bandwidth. So whenever we talk about FM bandwidth, we're always estimating, because the actual bandwidth is infinite. So if you were to plot, this is a spectrum analyzer, this is a frequency analyzer, spectrum analyzer, signal analyzer, network analyzer, they all mean the same thing. So this is the frequency axis. And you can see that the bandwidth of FM, you might think of that as the bandwidth, but then you could consider that to be the bandwidth or that to be the bandwidth. In fact, the bandwidth of FM is infinite. Okay, so there's an infinite bandwidth. So what we're talking about is something called the effective bandwidth. You might remember that from signals and systems in the first semester. So the effective bandwidth is where most of the energy resides. So if most of the energy resides between 2 frequency values, we call that the 98% effective bandwidth. And Carson generally said, Carson said that if we have something called wideband FM, where the modulation index beta is greater than 1, then we can approximate this effective bandwidth to something which isn't twice FM, which is what we'd have from AM, but it's twice AM times 1 plus beta. Okay, so at best, if beta was really, really small, you'd have 2 times FM. Okay, so this is an approximation. We call it Carson's rule in reference to John Carson, who not long ago actually came up with this approximation. It's just an easy way to relate the bandwidth used to the modulation index. And remember, in AM, the bandwidth is related only to FM, whereas in frequency modulation, the depth of modulation does make a difference because it affects the frequency deviation and the frequency swing. So now we're going to talk about 2 types of FM. There's something called narrowband FM. That's where beta is really small. So if beta is really small, then we can approximate the bandwidth to simply 2 times FM. Okay, so this is our approximation for narrowband FM. If beta is large, typically greater than 1, or in the region of 1 onwards, then that approximation won't work, and you'll need to use this approximation here. Now, even this is an approximation, because even in practice, for FM broadcasts where you have a frequency deviation of 75 kilohertz, for an audio message of 15 kilohertz, that gives you a modulation index of 75 over 15 equals 5. So in theory, regardless of what the carrier frequency is, your bandwidth, according to Carson, will be 2 times 1 plus 5 times 15, which is 180 kilohertz. Whereas in commercial broadcasting, we allow up to 225 kilohertz. Okay, so even Carson's approximation, we make allowances for that. So how does narrowband and wideband FM look in the frequency domain? Well, for narrowband FM, your bandwidth really is limited to that. So you've got your carrier frequency here, and you've got FC minus FM and FC plus FM. Okay, so these don't necessarily represent what you are familiar with in an AM spectrum, but the general shape is very similar. Whereas for wideband FM, if we're going to approximate that to be our bandwidth, then you're using that. So you've got your carrier frequency in the middle, then you've got your carrier frequency plus and your carrier frequency minus. So this isn't particularly useful, actually. There you go. So this is a slightly neater version of the relationships we presented earlier. So if you imagine that we have a single tone message, your instantaneous frequency for an FM signal, this is your instantaneous frequency, will be your carrier frequency plus some constant, let's put the constant there, some constant multiplied by your message. So this is simply your message. So this product of KF times AM, that's what we call our frequency deviation. Now your phase, remember, is the integral of your instantaneous frequency. So if you integrate that, you have that. So the integral of a cosine will give you sine, then you divide by FM. So you end up with that. And this quotient, delta F over FM, that's what we call beta. So this results in this really handy expression here, where for a single tone, or a single tone message, and by single tone, I mean we have a single frequency there, we can write our FM signal like that. And that's really handy because it means we can just find beta without calculation. It's sitting right there. Okay, so again, a recap of some of these expressions we've been using. So the general expression for FM, this is your message, that's an integral. For PM, you don't need to integrate your message. If we have beta in the order of 1 or larger, then you can use this approximation. It's Carson's rule. If beta is much smaller than 1, then even Carson's rule can be abbreviated to simply 2 times FM. And that's sort of similar to AM DSB bandwidth. This is an interesting observation, that if you double the signal amplitude, that'll double the FM bandwidth. Now I'll leave that for you to figure out why. So if I were to double the amplitude of that, it would double the bandwidth there. How does that work? How does doubling the amplitude of our message, so if you have your message like that, if you were to double the amplitude of the message, how would that double the bandwidth? Okay, so remember I just reminded you of DSB. Now, narrowband FM and DSB are both similar in the sense that there is a carrier term and they have the same bandwidth. Remember I showed you the spectrum, and you had a carrier term and you had upper and lower sidebands. And the bandwidth was twice FM. That's where the similarities end, because the carrier and the sidebands are not the same. You've got sine and you've got cosine components, so they're orthogonal, so they're 90 degrees out of phase. The amplitude for narrowband FM is constant, whereas the amplitude of AM varies. Now, this amplitude of AM, the fact that it varies, is fairly obvious because it is called amplitude modulation. That's where the message is encoded. It's encoded into the envelope, into the changing amplitude of the carrier. Whereas in FM, what's changing is the frequency and not the amplitude. So the amplitude is actually constant. Frequency varies. So the frequency varies for FM, whereas the frequency of a AM signal is constant. Okay, so you've got a couple of similarities and a couple of differences. Now we'll compare FM and AM at the end of the lecture, but this is just a quick comparison between narrowband FM and DSB or AM. A couple of quick questions for you. So this is an example from that textbook. If we had an FM signal given in that form, and remember this is very similar to the standard form of FM that we spoke about before. So if you're given a signal that looks like that, can you find the carrier frequency? So the carrier frequency, we're talking about FC. Where would you look? Do you look here, 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 or here? So the carrier frequency, that's your carrier frequency, should be right here. So your carrier frequency is 10 to the power 6 times pi divided by 2 pi. Right, we divide by 2 pi because we don't want it in radians per second. We want the answer in hertz. Now the modulation index, that's just beta, isn't it? So we could calculate beta, or we could just pull it straight out of the expression. So beta is right there, right there. Peak frequency deviation, so that is delta F. So delta F is just beta times FM. because that's the definition of beta. Beta equals delta F over FM. So beta we know, we just found that. What's FM? I mean, to find FM, you'd look for it right there. It's right there. So that's where you'd find FM. So FM is 1000 pi divided by 2 pi. And if you multiply that by 8, you get 4 kilohertz. Okay, so that's one example. There's a couple more. This is from the same book. It's just another example. So we're given an FM signal and we're told the carrier frequency. So that's FC. And we're given the frequency deviation. So that's delta F. And we're asked to estimate the bandwidth. And we're told that FM is either 500 kilohertz, 500 hertz, or 10 kilohertz. So we would be using Carson's rule, but first we would need to find the modulation index. So let me try this. So the modulation index is the ratio of delta F to FM. So in this case, it would be 50K over 500K, which is 0.1. So we have narrowband FM. Because beta is much less than 1. So your bandwidth will be twice FM, which is 2 times 500 kilohertz, which is 1000 kilohertz. So that's the 1 megahertz. Okay. So if we move on to B, beta in this case is 50K divided by 500. Or we can write 500 as 0.5K. So that'll give you a modulation index of 100. So that's clearly much bigger than 1. So we have wide band FM. So your bandwidth will be, using Carson's rule, 1 plus beta times FM. So that's 2 into 101 times 500. So that's 100, or should I say 101 kilohertz. So there you have, so it's an approximation. It said approximated. So it's actually 101, but an approximation of 100 is acceptable. And finally, for the third section, beta equals 50K over 10K. So that'll give you 5. So again, we have wideband FM because 5 is greater than 1. So your bandwidth using Carson's rule is approximately 1 plus beta FM. So that's 2 times 6 times 10k. So that's 120 kilohertz. And that's your third answer there. So that's how you would answer a question like that. Fairly straightforward. One last example. This is from a different textbook. Again, we have a FM signal, but this time instead of having one term, we have two. So we can't use the regular expression that we used a couple of slides ago. So we can't just use this expression to find beta and FM. So it's a little bit more work involved this time. Now the first section says find the power. Now to find the power of a signal, where do you look? Remember, this signal it's a cosine and it has a constant amplitude. It's a cosine with a constant amplitude. The amplitude is 10. So to find the power, you would be looking at the amplitude squared divided by 2. So it's 10 squared divided by 2. So that's how you would find the power. You don't need to involve the frequencies at all because it's a constant amplitude cosine. The next section says find the frequency deviation. So that's delta F. So where would we look for that? So for the frequency deviation, you'd be looking at the frequency. So this is the angle. You'd be looking at the instantaneous frequency and the maximum deviation of the instantaneous frequency from FC. So you can find that. It's to find the instantaneous frequency, remember you need to differentiate the phase. So it's the derivative of the phase. So the sine will give you a cosine, and the cosine, these sines will both give you cosines. But when you differentiate, you need to multiply by the coefficient of t there. So you would have 5 times 3,000 plus 10 times 2,000. And there's a pi right there. We need to remember that. And because the answer needs to be in hertz, you divide by 2 pi. And remember, we're not looking at the instantaneous frequency, we're looking at the maximum frequency deviation. So we need to subtract omega c, or omega c over 2 pi, which is fc. And we can assume that these two signs will both be equal to 1 at some point in time. So you can add the 5 and 10 together. So that's why we allow ourselves to do that. And if you calculate that, that should give you 12.387. And that's in kilohertz. The next question is find the deviation ratio. Deviation ratio is just another way of saying modulation index. Okay, so how do we find beta? Now remember, beta is just the ratio of delta F to FM. That's why they call it the deviation ratio, because you've got the maximum frequency deviation there. So that's 12.387 divided by FM. Now, where do we look for FM? Where do we look for FM? Is it this, that, or that? Well, it's certainly not this, because that's the carrier frequency. And that's one thing we're not interested in. Even though that's given in the question, we're not interested in the carrier frequency. So let's cross that out. So FM is the higher of the two. So the greater of the two, that's the one which will determine the message bandwidth. So even though 3000 looks like it's bigger than 2000, here we have a pi. So 2000 pi, that's your FM. So FM will be 2000 pi divided by 2 pi, which is 1 kilohertz. So if you divide that, you'll get 12.387. So that's your modulation index. And then it says find the phase deviation. The phase deviation is easy because you don't need to differentiate or anything. All you need for the phase deviation is to look at the angle there and see what's the maximum deviation from omega CT, because that's what the normal cosine would be. So what's the maximum deviation? It's when this would equal 1 and this would equal 1. So it's just 5 plus 10. 15. And the unit is radians. So the phase deviation, the unit for phase, is radians. Okay, here I have a couple of YouTube videos that I wanted to share with you, simply because there is a common perception that radio is dead and nobody needs radio. The internet has killed radio, and in a world where we have Apple Music and Spotify, radio is outdated technology. And there is truth to that. But nevertheless, in addition to simply listening to the news and entertainment and traffic and music while people commute in their cars, etc., there are very serious reasons why radio still exists. So I've titled this Radio Saves Lives. And there's two very quick YouTube videos I want to share with you.
On today's Hurricane Gear Test, we're looking at a classic emergency preparedness item, a crank-powered weather radio. This is the Midland ER310, along with the smaller 210 model. And I normally avoid weather radios, to be perfectly honest. I think it's one of those things that sounds really good, but it never really works, or people just don't really seem to use them. But this one really does have some features that I think should make you consider it. Let's start by clarifying. It doesn't have just the NOAA weather radio frequencies. It will also let you tune in your favorite AM and FM stations. So that's something that you always want to make sure and look into when you want to buy an emergency radio. It will also have several other functions, including a flashlight that you can have 2 different settings, as well as be able to become an SOS flashing beacon. And it has an ultrasonic dog whistle, which is something new for me. I've never heard of that before. And it's actually supposed to help in a situation that might involve a search and rescue team that has dogs. So you wouldn't have to be yelling the whole time. You could just activate this dog whistle. But it's the power source that is really the standout for me on this device. It comes with a rechargeable battery, which of course you can use the crank to recharge, but it also has solar panels on the top, which help it during the daylight hours to recharge. And when you have time, you can also simply pre-charge this by putting a USB cable in the side and then plugging that in and getting it ready before the storm might come along. But wait, there's more. Also, you can actually put standard AA batteries in here if all of those other options won't work for you. But the final feature of this particular tool is the reason that this gets a Cat 5 from me. You can recharge your cell phone with it. The 2600 milliamp hour rechargeable battery that's in here should give you at least one full charge on your cell phone. And if you need more, you can always just crank away. I give the Midland ER310 a Cat 5 out of a possible 5 on my Hurricane Kit priority scale. It is loaded with features that you need in your Hurricane Kit. The list price is about $60, but the smaller model is slightly cheaper. Do you have an emergency radio in your Hurricane Kit? Leave me a comment on my Facebook page. John Dawson, Fox 26.
हामीलाई निन्द्रा पनि लागेको छैन हाम्रो 7-8 महिनाको बालबच्चा सुतेर बसेको छ चिसो भएको छ निमोनिया हुन्छ विभिन्न प्रकारका डिजिज लाग्छ
भूकम्पबाट प्रभावितहरूले उद्धार र राहतका लागि सरकारलाई कहाँ गुहार्ने मन्त्रीज्यू?
अहिले बेलुकीदेखि नयाँ टेलिफोन लाइन सुरु गर्न थालेका छौँ 1 2 3 4 मा डायल गरिसकेपछि तपाईलाई जुन किसिमको सेवा चाहिएको छ पालको सेवा छ कि पानीको सेवा छ कि
मिनरल वाटर सप्लाई गरिरहेको छ त्यस्तो मान्छेहरूलाई पनि हस्पिटलमा पनि गरिरहेको छ हैन त्यो पानी खाए भयो अथवा सकिन्छ भने बोइल गरेर खाने बोतलको पानीमा मजाले घुल्ने 10-15 मिनेट घुल्ने मजाले त्यसपछि घाममा राख्दिने सोलरको सिस्टम कम्तीमा केही कीटाणुहरू कम चाहिँ सोलरको पानीले कम हुन्छ त्यसलाई सोडिस भन्छ
Remember I said the second half of today's lecture, or less than half really, is where we'll talk about demodulation. So demodulation is how do we extract our original message from our bandpass signal? How do we recover our original message? So for AM we would use the envelope detector, for DSB we would use a coherent demodulator, for FM what do we use? So there's many different ways of doing this. In this module, I'll concentrate on two. One is called the discriminator, and one is called a zero crossing detector. In practice, we often use a phased lock loop and other kind of detectors. But because these two are fairly easy to follow and to understand, I'll limit this lecture to the first two. So think of the FM signal and think, where is the message? Where's the original modulating message? It's in there and it's being integrated. Remember we said instantaneous frequency, or frequency is the derivative of the phase, and the phase is the integral of the frequency. So to get the angle, we take the original message and we integrate it. So it makes sense that if you want to recover your message, you would need a differentiator. You would need to reverse the integration. So what we do is we take our FM signal and we apply a differentiator. And after differentiating, what you'll have, so the derivative of a cosine is a sine multiplied by the derivative of this argument. The derivative of this argument will have this constant term here, we'll have this constant term here, but we'll also have our message there. So your message will actually be multiplied by your cosine or your sine. So what that multiplication will give you is a kind of amplitude modulation where the envelope of the carrier is now your actual message. So this message is the envelope. So notice that here we have a frequency that changes with time. This frequency continues to change with time. So here the frequency is high, low, high, low, high. Same here, your frequency is varying. But now we've managed somehow to pull this out. We can use a normal envelope detector to then recover the original message. So what we have here is something that looks like an AM signal. It's not a true AM signal because the frequency is still changing, but it's a pseudo AM signal. It looks like an AM signal. The message is still encoded into the amplitude or into the envelope. And that's enough for us to be able to recover the message signal using an envelope detector. So that's the first kind of detector. That's the discriminator or the slope detector. Why do we call it a slope detector? Because that's essentially what you're doing. When you take the derivative, when you apply this differentiation, what you're doing is you're finding dy by dt, i.e. you're estimating the slope, the gradient. The other type of demodulator we use is something called a zero crossing detector. Now remember, we keep saying that the message isn't encoded in the amplitude, it's actually encoded in the frequency. So you've got high frequency, high, low. What we can do is look at these zero crossings. See, these zero crossings are really close together. These are less bunched up. These are close together. And these are less so, etc. So if we can detect these zero crossings, we can then recover our message. And that's really valuable because noise might cause the amplitude here to change. So the amplitude might be affected by noise, okay? Noise will affect the amplitude, but we don't really care because we're not even looking at that. If we look here, it's much less likely that the noise is going to affect the zero crossings. So what we can do is block out all of this bit using some kind of a limiter. So all of these higher amplitudes we can block out so we can focus on those zero crossings. And then by differentiating, that gives you the gives you very high values. It gives you spikes whenever you have a steep gradient, dy by dt. So all of these steep gradients will give you these spikes, which you can then rectify, and then you can use these to generate pulses. And if you integrate, if you add the area of these pulses together using a low-pass filter, that will allow you to recover your message. And that'll give you a better approximation of what you would get using an envelope detector. Okay, I don't want to go into too much mathematical detail. That's enough really for the zero crossing detector. I wanted to say a few final things about AM versus FM and about the future of FM. So, even though we've said that radio in general is becoming less and less popular, it's far from being dead. But having said that, FM is slowly being discontinued. It's being switched off. Okay. Okay, so FM is being replaced by digital audio broadcast, DAB. Okay, so again, I've got a couple of YouTube clips to share with you. One is about Norway, where they've actually turned off this is, I think, back in 2015 or 16, they turned off their FM signal. They're the first country in the world to do that. And there's a short clip talking about when will the UK do the same.
Norway has become the first country in the world to shut down national broadcasts on its FM radio network. From now on, all the state broadcasters' radio programmes can only be heard via DAB, or digital audio broadcasting. The Scandinavian country made the final switch to DAB on Thursday, when the last FM signal was switched off in the counties of Troms and Finnmark. There'll be new products over the next few months. You'll have touchscreens and it'll be possible to let you read the text on the display. But older people in particular might not be so familiar with digital radio. One Norwegian newspaper reported that national public broadcaster NRK has lost a fifth of its listeners since January, when the process of switching from FM started. Some technical problems have also been reported, but the government says DAB radio will save money, allow for more broadcasters and ultimately sound much better.
Change how you listen to the radio are underway. Like the digital television switchover in 2012, the digital radio transition will see FM and AM broadcasts replaced by DAB. Unlike traditional analogue radio, you can listen to digital stations via the internet and TV, and on a DAB device. It offers a greater choice of stations to listen to than FM, but the devices are more expensive. Reception can be patchy, and many older radios and car radios don't have the technology fitted. The government says it will start a wholesale radio switchover when 50% of us are listening digitally and DAB signal coverage is as good as FM. Digital listening has now passed the 50% threshold. Once the switchover announcement is made, you'll still have at least 2 years until it's put into action. And while all national and most regional stations will stop using FM to transmit, some smaller local and community stations will continue to broadcast in FM. To find out how to stay connected when the UK switches to DAB, visit which.co.uk/digital radio.
Final slide for today's lecture. I want a quick comparison of AM and FM. So there's nothing really new in this slide, but this is to bring a few things together side by side so we can note these differences and similarities. So AM is at a much lower frequency than FM. So that's important to note. So the megahertz is 1,000 kilohertz. So there's a significantly higher frequency for FM. And this higher frequency means, on the one hand, the antenna sizes can be smaller, but more importantly, it means that we have a limited range. And that's because the only way that such relatively short wavelengths can be received is through line of sight reception, where you have your transmitter and your receiver, and there is a direct line of sight. So that means that a transmitter there will only have a range of approximately 40 miles, or roughly 60 kilometers, because the signal is unable to propagate around the surface of the Earth. That's what would happen if we had longer wavelengths, and it's unable to bounce off the upper atmosphere. And again, that's what we would do if we had lower frequencies. So AM can do that, FM can't. Now, that has nothing to do with the modulation format. It's all about the frequency. And it just happens that AM uses lower frequency, and therefore it gets away with these tricks here, whereas FM can't. Now, in terms of bandwidth, we know that the bandwidth of AM is just twice the message bandwidth, whereas for wideband FM, it can be much higher. It's typically around 10 to 12. So we're talking about, for an audio broadcast of 15 kilohertz, so if we had a message of 15 kilohertz, it means our message bandwidth is significantly higher than 10 times that. So it's in the order of 200 kilohertz. So 200 kilohertz, compare that to 30 kilohertz. So it means there's much more bandwidth is being used. So we say that the bandwidth efficiency is low for FM compared to AM. In contrast, the power efficiency of FM is high compared to the power efficiency of AM. And we know that because there's all the wasted power in the carrier. Now, you know that in AM we have a limited modulation index, where the modulation index has to be greater than 0 and less than or equal to 1, whereas in FM your modulation index isn't really limited. In practice it will be, but there's no inherent limitation. Now, in AM, the transmitter and receiver circuits are generally quite simple. All you need to do, really, to transmit AM is to multiply, or to add DC, then multiply by a carrier. And to receive it, you can use an envelope detector, which is the simplest circuit in the world, or a coherent demodulator, which is simply a multiplier followed by a low-pass filter. Whereas for FM, both the transmitter and receiver circuits are quite complex, so that adds to the cost. A very important one is that we have a better reception quality for FM. And the reason is it's less susceptible to noise. And the reason for that is because the information is encoded in the frequency, or the zero crossings, and not the amplitude. Whereas AM is susceptible to noise. Therefore, the audio quality, the quality of the received signal will be poor. So that's a quick summary of AM and FM, and that's the end of today's lecture. So what we covered was bandwidth and Carson's rule. We looked at the future of FM, advantages and disadvantages of FM compared to AM, and we spoke about two different types of FM demodulation. Next lecture, we introduce digitization. We've spoken a bit about that before, but this will be our next lecture before we start talking about digital communications in the last 3 lectures of the module. I hope you found that helpful. Until we meet again, stay safe.